Hello and welcome to the final lecture and the final session as part of the machine learning module on the Health Eye course. In this lecture, I'm going to talk about some of the new research in machine learning that is changing the field and the kind of things that are done. But I also want to talk about some of the challenges and some of the issues that are raised by this work, particularly the more recent work. So I'm going to start by going through three relatively recent developments in machine learning research. The first is deep learning, which now I guess it's not that recent. It's been around for about 10 years. But also what are called adversarial networks, which are slightly newer. And then reinforcement learning, which has been around for a while, but has only begun to have a real impact relatively recently. So I'm going to start with the topic of deep learning, and I'm going to introduce it by way of a comparison with the older forms of shallow neural networks. And this slide should be familiar to you from the lecture on neural networks. And you'll remember that these have a set of input nodes which are linked to hidden nodes, which are in turn linked to an output node. And the network learns by being presented with examples of sets of features, and then the weights in the network are altered in order to improve the classification accuracy until it arrives at some form of optimum performance. And the way that the weights are adjusted is via a mechanism called backpropagation. And the difficult thing is that the deeper the network, the more hidden layers you have, the harder it is for the network to learn the intermediate classifications in the hidden layers. So backpropagation is a very efficient method of training in a very, very shallow network, but it becomes hard to make it work over a deeper network. And what happened in the, I guess, around about 10 years ago, maybe slightly longer, is that people developed ways of using a kind of neural network to learn features that could be input to something similar to this kind of classifier. So you would have a set of layers in the network which would take the raw features, the really low level features, and will be able to learn the appropriate derived features that could be then made the basis of a classification like the one you see here. So what would happen in this kind of network, which actually, I took this diagram from a paper from 2004, I think, and the features F1 to F14 were measured by the author. They were kind of calculated. There were statistics about an image. What you have now is a network where you can actually feed into it a raw image. There's the pixels, which are the raw data on which the classification is based. But the bottom layers of the network are all about finding the right sets of features at a level of a few pixels in order to drive forward the classification. So here's an example of an architecture from a paper that 5 years ago that uses this kind of network. I'm not going to expect you to go into the detail of all of this. That's kind of at a level beyond which we have time for in this module. But I just want to explain the sort of roughly the way this works. So if you look at the top left, you'll see that there are three vertical lines, and one that says 1 at the top, 164, and the next one says 64. So the first one's the original input image, which is 572 by 572 pixels. And then the next image, which is created by, which is learned from that by a neural network, is a set of 570 by 570 feature vectors, and in fact it's 64 different feature vectors. So for each pixel, each position in the image, you're learning a set of 64 different features. So the features will be really simple. There'll be things like lines or edges. There'll be just things that you can identify from a network of maybe 9 or 15 pixels. And then that sort of stack of feature images is then analyzed again to create a set of feature images of the feature images. And then these are then reduced in size, but the feature vectors are doubled. So you see what happens in the next phase is you've got 282 by 282 pixel images, but in a stack of 128 features. And again, you learn a feature image from that. And this keeps on going with the feature vectors getting bigger and the images getting smaller until you've arrived at a very, very enormous feature vector, which is then made the basis for some classification. And then that's upscaled back to the scale of the original image to create something that the human can look at and see a segmentation. And the reason I picked that image was that's been used in a very prominent piece of research looking at optical coherence tomography. And I've given an example of an optical coherence tomography image here. So this is an image of the retina, and what you see is a slice. In image B, you see a slice through the retina, and in image A, you see what's called the en face view, which is the kind of face-on view. What I want you to look at on this slide is the segmentation of one of these or three of these slices by an algorithm using the network I explained earlier. So on the left-hand side of this slide, you see three different slices through OCT volumes. In the middle, you see human experts who've attempted to draw around the areas of interest in these images. And on the right-hand side, you see the algorithm segmentation. And you see from this very, very clearly that the algorithm agrees pretty well with the human experts. And this is a slide of the performance of that algorithm on data. This is an ROC curve, so we're plotting the accuracy, the percentage of correct decisions on the x-axis, and on the y-axis you've got the false alarm rate. So it's effectively an ROC curve. And on the right-hand side, we're zooming in onto the top left-hand corner of the ROC curve, and you can compare the retinal specialists and the optometrists' performance with that of the algorithm, and you see that it's doing pretty well. I think you'll notice for some of the, I think for all of the human readers, there are two measurements given. One shows how they performed when they were given the same information as the machine, and one shows how they would perform when they were given that information plus the additional clinical information which the human would typically have, but which the machine isn't able to take advantage of. And you'll see that the additional clinical information improves their performance by and large, but even with that information, they're still not outperforming the machine. So this was a hugely widely reported study, partly because the team are associated with Google, but it's seen as being an example of where deep learning can accomplish a significant task in healthcare better than a human. And certainly from a UK perspective, this is really important because ophthalmology is the largest single source of outpatient appointments, and OCT scans are the most important image in the management of retinal diseases, which is obviously a significant proportion of those outpatient appointments. So at the moment, retinal specialists are drowning in OCT scans. They're simply not able to acquire them, to interpret them as quickly as they can be acquired. So the idea that this can be, even in part, automated is really exciting. The next category of new research in machine learning that I want to talk about is generative adversarial networks. This is a really exciting, relatively recent development in neural networks, where you've got two different networks working in competition with each other. So you've got one network which has been trained. It's quite different to the kind of networks we've talked about before, because it's not learning to classify one kind of image as disease and another kind as not disease, for example. It's learning to generate images. So it's learning a mapping from random noise to something that looks like an image. And it does that because it's being trained against a real images, but in an interesting way, in that it's being put in competition with a discriminator network, which is learning to distinguish between the images generated by the generator and real images. So the generator generates its output, and at the first it's going to be pretty random, but its performance is assessed against its capacity to deceive a discriminator. And the discriminator at the beginning, its performance is sort of random as well, because it's not trained. But as it gets better and better at discriminating between real images and fake images, it kind of learns to generate the output, which helps to train the other network. And at the end of the process, you end up where the generator has learned the kind of the latent space of the class of images that you're interested in. And that's really important, because you can use that latent space as a basis for a classification. So what you see here is, on the bottom you see a set of sections from chest x-rays, and at the top you see synthetic images which we've generated, and you're not going to mistake one from the other. These networks are hard to train, and not in the sort of intellectually hard, but in terms of the amount of computing power they require, and so we're hoping this will get better. But what we've found is that model, which was trained on a very, very large number of normal images, is able to build a latent space that we can then use as a measure of normality. So we can then test that, we can use the parameters of that network to test to see whether another image is normal or not. And this is really important, because in chest x-rays, for example, we have huge numbers of normal images that we can use to train, but we have a very small number of disease cases. For example, we've got 100,000 normal chest x-rays and only 300 cases of TB in our data set. So it's not really practical for us to try and train a neural network in the classical way, because the imbalance between the normal and the abnormal is so huge. And I just wanted to show you this this isn't anything to do with healthcare or any kind of medical imaging application. But I think this is really compelling. So that image you're seeing there is not a photograph. It's not of a person. So somebody, the person behind this website, has trained a generative adversarial network on pictures of human faces just taken from the web, and I imagine a very, very large number of human faces. And it has learnt a latent space, and you are seeing a visualization of a random point in that latent space. And it looks incredibly realistic, and it's quite shocking. If you go to the website and look at a lot of them, you'll see some problems. And there are some people who are wearing what I call Schrödinger spectacles, and there are other people who seem to have something on their head that's on a continuum between hair and a hat, but isn't one or the other. And it's surprisingly easily confused by earrings. But it does show just how good these networks can become at generating synthetic images. Some people have talked about using it in healthcare to generate synthetic images of chest x-rays or retinal images, or things that we can use in research. I'm not convinced that that's necessary, because it's not. It's hard sometimes to get access to real cases, but it's not that hard. And the third example I wanted to draw to your attention is something that's been received a lot of attention in the last few years, which is reinforcement learning. And this is neither supervised learning nor unsupervised learning. It's something a little bit different. And it's very good at playing games. It's very good at navigating its way through sort of sequences of decisions in order to maximize some kind of outcome, which is exactly what you're doing when you're playing a game. And the way it works is that you have you model an environment, and you have an agent that's operating within that environment, and you give it the capacity to take certain actions that alter the environment, and then that altered state at some makes possible a different range of actions possibly, or it enables you to receive some reward. And what the algorithm does is it enables you to preferentially select the actions which will alter the environment in order to lead to new states, which ultimately will lead to a maximization of reward. And this shows this a kind of typical reinforcement learning algorithm set up in a little bit more detail. So again, you've got the agents in the environment, but what you're seeing is that the agent has what we call a policy, which determines what actions it thinks are appropriate. And that policy is being updated by the learning algorithm as the learning algorithm absorbs information about how the actions are changing the environment and how rewards and different states are being created as a result of those actions. As I've said, these algorithms are extremely good at playing games like chess and Go or StarCraft or Atari games or whatever. And if you think about the kinds of problems which they're going to be well suited to, it's not immediately obvious that there are lots of applications in healthcare for this kind of technology. I mean, they are being used. They're not just used for playing games. They're used, for example, to control the heating in air conditioning, the air conditioning, the heating, and so on in server farms. So Google uses them to reduce its power consumption by optimizing allowing the algorithm to change the configuration of the different machines that are used to control the environment in order to minimize the costs. And apparently that they've had a significant impact on Google's environmental impact and its costs. I've shown here a reference to a paper which does give an example of reinforcement learning used in healthcare, and that's in the area of sepsis control. And I think where you can see healthcare as examples in healthcare of an optimization problem, where you're trying to alter the parameters in order to optimize some outcome, then you could apply reinforcement learning. And it may be, for example, that some treatments can be seen in that way. So there may be a room for reinforcement learning in learning how best to select the treatment frequency for some course of drugs or so on. The worry I have there is that I'm not sure it's going to be easy to give them enough data to do that. So the great thing about games is that the amount of data you can obtain is almost infinite. So you can just set the algorithms to play chess against themselves, and you can generate billions and billions of games relatively quickly. Obviously, with something like chemotherapy, for example, you're only going to know that the trajectory of one patient. You can't alter the variable and then see what happens to that patient. You only get one shot at that patient's experience. And obviously you can put together a large number of patients, but there are going to be lots of variables there. So I'm not sure that it's going to be easy to apply reinforcement learning in healthcare. In closing this session, I wanted to look at some of the issues that arise when we think about how machine learning could be applied in healthcare. And I've picked 4 as being particularly salient or worthy of attention or things that have been talked about relatively recently. Fairness, safety, the role of the private sector, and the impacts that this technology might have on the practice of healthcare. So the first of these is fairness, and this is something which researchers in machine learning are increasingly conscious of, and it's being debated a lot in the media and in academic circles, and it's the kind of thing that gets talked about at conferences and so on. And I've picked as an example of the way this has been highlighted in research, a paper by Obermeyer et al., which the reference is on the slide, where they found evidence of racial bias in an algorithm that's used to guide health decisions. So this is an algorithm that's available commercially in the United States and used by health providers. And the aim of the algorithm is to cut costs. And what the algorithm does is identifies patients as being suitable for an intervention, the aim of which is to cut costs. But the way it cuts those costs is by identifying people who are at risk of readmission to hospital and then giving them extra care in order to prevent them from being readmitted in order to cut costs. But because it's a very sort of focused on the financial outcomes, the algorithm actually isn't about health, it's about money. So it's looking at patients who are essentially it uses cost as a proxy for health needs in its assessment of how sick somebody is. And what you find is that in the US, white patients seem to be incurring higher costs than black patients who have comparable levels of disease because of the systemic inequalities in American society. So the result of that is that the white people are seen by the algorithm as being sicker than they actually are, and so they're more likely to be identified as appropriate for this intervention. And this intervention could be characterized as giving them more, perhaps better care. But you remember that the aim of the intervention is to prevent these people from being readmitted to hospital in order to save money. So its end goal isn't better care, but less expense. And maybe if that's your metric, then using costs as your sort of primary indicator of who's at greatest risk is better, as a better measure than their health state. But nevertheless, the algorithm is behaving in a racist way, and that's enough for it to be problematic. That's an issue about fairness. This is an issue about safety. So this is an algorithm which is provided in the UK by a company called Babylon Health, and it's an app on your phone, and it allows you to connect with a GP for a video conference. So you pay a monthly subscription, and it means you have a more convenient way of accessing a general practitioner than the National Health Service, than the system that's provided by the state. It does have within it an app which uses artificial intelligence to identify from somebody's symptoms what the likelihood is of them having various diseases. And it acquires information about those symptoms by asking questions, and it decides what question to ask on the basis of how you answered the preceding question. So you kind of have this interaction with a chatbot, and at the end of your interaction, it has a certain number of answers that you've given, and it associates those with symptoms, and it knows something about the probability of diseases and how the probability of diseases is for patients with different configurations of symptoms. And then it tells you whether or not you should seek further advice or not. But I've put on this slide two snippets. One is from the sort of terms and conditions for Babylon, in which it states that as far as its lawyers are concerned, its output is not medical advice. I think that's a very interesting statement, because if you're giving it information about your symptoms and it's telling you whether or not you need to seek help, I think a lot of users would think that they are actually receiving medical advice, but as far as Babylon are concerned, they're not. And the reason for that is quite clear, that if Babylon was giving medical advice, it would have to pass a much higher degree of safety testing than it has. And what you see on the other panel is that somebody tweeting a complaint that the chatbot has asked an unintelligent question, in that it's considering whether or not somebody who's already said that they've had their appendix out might be suffering from appendicitis. So it's an impressive tool. It's a business model that seems to work well. They seem to be attracting a lot of custom, but it only really gets through the regulatory framework in the UK by pretending that it's similar to a website or a book or some source of information. It's not. It says it's not actually providing advice the way that a clinician would, and I think that's a pretty tough line to draw, actually. So questions about safety arise in that instance. Question of fairness arrived in the previous instance. And now I'm in a couple of slides to talk about concerns that some people have about the role of the private sector in the application of machine learning in healthcare. And I've tried in this graphic to show how data flows around the system as machine learning is developed and applied. So the idea is that the patient's in the middle and they provide their data through either through interacting with the system or by talking to a clinician, but something happens and as a result data is recorded about them in the system, and they do that willingly because in return they receive healthcare. So when you're talking to your GP, you're happy that your GP records information on a computer because you know that helps you receive better care. But there is this idea of the data surplus, so more data is the data is used for some other purpose, not just to help organise your care and make sure you get better care. And some of that is extracted from the NHS by third parties and then sold, for example, to researchers like me, who then use it to produce outputs, some which hopefully benefit patients, some which hopefully benefit the NHS, but that has to be paid for. Because we have to pay for the data. And so you have this kind of transactional model whereby people who are working with the NHS are able to get data out of it and are then making that available in return for a fee. And I think there's some concern about that because the patients whose data this is, in some sense, aren't aware that this is happening, and it's and not all of them would be comfortable with it. This is another kind of transaction which I think is causing concern. This is the idea that the data is going not to researchers but to companies like Google or to Babylon, and that they are then using that to develop services, which again, that it's a good thing that these services are valued and are useful and they benefit patients and they benefit the NHS. But somebody has to pay for them because these are companies. They're not doing it for the love. And I think at the moment that there's some concern about this because essentially the data is being given away. The third parties who I talked about before, they wouldn't be allowed to make money available for a fee to a commercial entity. That wouldn't be allowed within the ethical framework that we operate in. But what you get is that these companies are acquiring data from the hospitals or from researchers, and that there's no mechanism whereby the profits that they will eventually recoup are being used to fund are being fed back into the people whose data they obtained. And finally, I want to leave you with some thoughts about what the automation that machine learning will enable will do to the working lives of people in healthcare. And this is a report by Eric Topol, which was prepared a few years ago, and he talked about the gift of time, the idea that the automation of tasks would liberate the clinicians from having to perform a number of the less interesting things that they currently have to do, and this would enable them to spend more time on the tasks that motivated them to come into medicine in the first place. So the radiologists wouldn't be looking at screening mammograms anymore because that can be automated, but they would be talking to women with breast cancer, and they would be providing better care because they weren't having to do the kind of the more simple and automatable tasks that currently take up much of their time. And I put this in as a kind of reply to the optimistic conclusion of that report, because I think it would be naive to imagine that the drivers in the system are actually going to make doctors' lives better and allow them to deliver better care. It's much more likely that those drivers are going to be used to maximize efficiencies and to save money. because that's the way that the system is set up. That's what it's set up to optimize. And here's an example of technology being used to dehumanize what ought to be a very personal interaction. And I think there's a concern that machine learning might lead to more of this rather than less. And I put this in. This refers to work that was published very recently, and if you search for it, you'll find it online. It's work that Google did on the analysis of breast X-rays, and they found that their algorithm performs as well as trained radiologists at identifying cancer on images. But the concern here is that this might improve the effectiveness of screening in terms of the detection of cancer, but it wouldn't necessarily improve the effectiveness of screening in terms of the saving of lives, because what it might do is lead to the discovery of a great deal more disease that's not life-threatening. Because the more you look for disease, the more you find, and the more you find, the less likely it is that you found the disease you need to find. So everybody will have, the beginnings of a cancer somewhere in their body. Most of them won't develop to be a life-threatening tumor. But if you're constantly investigating at greater and greater detail, you're going to find more and more of the tumors that aren't life-threatening. So I think that's a concern, particularly where there's something differential in how the screening is being applied. So at the moment, for example, you can buy an app on your phone which will take a photograph of your skin and say whether or not it thinks you should see a dermatologist. And if those apps are being used largely by wealthy, relatively healthy people who are concerned about their well-being, it may be that actually the capacity of dermatologists to deliver care to the people who really need it is degraded by the fact that they have to also deal with all these other people who actually, by and large, are perfectly healthy. Last point on the subject of the impact of AI on the practice of healthcare is to draw attention to this piece which appeared in the New Yorker a year or two ago, called "Why Doctors Hate Their Computers." And I think this is a really important part of the story, because the impact of the current generation of IT on clinical work has been almost entirely negative. I mean, there are good systems, there are things which have been done which have been helpful, but actually the way in which it's changed the day-to-day practice of medicine and the way doctors feel about their working lives is really it's been really destructive. And I think we need to get that right if we're going to build systems which are improving the quality of the practice of medicine as well as the outcomes from medicine. It's in some ways it's hard to see how that can be achieved. And I'd say there's a concern around machine learning, artificial intelligence, that the robots are going to take away all our jobs. And I think there's another concern which isn't articulated so often, which is that it may be in the future your job is being done by a robot, but the real problem is that the robot is you, and that you are being asked to fit into a world which is designed so that some tasks can be automated. But in order that some tasks can be automated, you are having to perform your work within more and more rigid and constrained pathways. So as a doctor, you're no longer writing, you're typing. You're no longer typing, you're selecting items from drop-down menus, and you're doing that in order that the workflows further upstream can be automated. But it makes your life it feels that what you're doing is automated, even though it's you doing it rather than a computer. And I certainly feel unconscious of that in some of my work as an academic, in terms of grading assignments and so on. The tools that we use are actually constraining us to make us more efficient, but actually the job becomes less enjoyable because of the way we're having to do it. So I just want to close this lecture with just to review the bullet points. So I introduced 3 different research areas in machine learning, deep learning, reinforcement learning, adversarial networks, and I didn't talk about any of them very long. I didn't go into the detail of them, but it's important that you are able to recognize these terms and have some idea of what they mean. And I talked about sort of issues around fairness and bias in machine learning, and also about how machine learning affects the flows of data around healthcare and the way in which we work. So I hope that was interesting, and I hope the modules as a whole has been enjoyable, and good luck with your assignment.